This video lesson covers section 1 and 2 of our thermal physics lecture notes. Our lecture notes has a lot of content. Some are more important than others. The objective of this video lesson is to highlight and elaborate on the more important concepts. For this chapter, we need to differentiate macroscopic and microscopic properties. As an example, let's talk about macroscopic and microscopic kinetic energies. Suppose the mass of the system is big M, the speed of the system with respect to the Earth is V, then the macroscopic Ke of the system equal to half mv squared. Now, suppose there are n molecules inside the system. The mass of each molecule is m, and the average speed of each molecule with respect to a point inside the system, such as its center of mass, is c. Then the microscopic Ke of the system is half n mc squared. The value of V will not affect the microscopic kinetic energy of the system. So microscopic refers to those properties that are related to the molecular structure of the system and the degree of molecular activity. State of a system. Okay, the properties of the system that specify the condition of the system is called the state. For an ideal gas, we define the state of the system by 4 physical quantities, namely pressure, volume, temperature, and amount of substance. The equation of state, PV equal to nRT, states that the state is defined once we know any 3 of the above quantities. So if you know 3 of them, then the 4th one will be defined. R is a constant, so it's not a variable. The next important concept is thermal equilibrium. Two objects in thermal contact are said to be in thermal equilibrium when there is no net exchange of heat energy between them. So in this chapter, if two objects are in thermal equilibrium, they have the same temperature. So heat is defined as the transfer of thermal energy between two objects due to a difference in temperature between them. The Zeroth Law of thermodynamics. Why do we need the Zeroth Law? Consider 3 objects. Objects A and B are iron blocks. Object C is a magnet. A and C attract each other. B and C attract each other. However, that does not imply that A and B attract each other. In this case, A and B are iron blocks and they do not attract each other. It is different for the case of thermal equilibrium. Suppose A and C are in thermal equilibrium and B and C are also in thermal equilibrium. Then by the Zeroth law of thermodynamics, A and B are also in thermal equilibrium. So if C is a thermometer, then when C is in thermal contact with A, you measure a particular temperature. When C is in thermal contact with B and it measures the same temperature, then we know that A, B, and C are all in thermal equilibrium. So this concept allows us to use something called the thermometer to measure temperature. And that will determine whether two objects are in thermal equilibrium or not. Empirical scale and absolute scale. Empirical means based on experiments or observations. We define the temperature of pure melting ice to be 0 degrees centigrade. We also define the temperature of steam as standard atmospheric pressure to be 100 degrees centigrade. The centigrade scale, as defined above, is an example of an empirical scale. This scale depends on some physical quantities, namely that of pure melting ice and steam. Absolute scale is based on some physics theory. The ideal gas scale is an example of an absolute scale. Note that the ideal gas is a mathematical model created by scientists to help understand real gases. Examples of real gases are hydrogen, oxygen, nitrogen, helium, air, etc. In practice, the ideal gas model is able to describe real gases at low pressure very well. Section 11.3 will discuss the ideal gas in more details. The Celsius scale, to convert temperature measured in degrees Celsius to Kelvin, we use this equation, T is equal to temperature in Celsius plus 273.15. So that means 0 degrees Celsius is equal to 273.15 Kelvin. Okay, next we look at heat transfer, specific heat capacity, and internal energy. Now for this chapter, there are two important equations for heat transfer. The first one is Q equal to mc delta T. This is when there is change in temperature or there's no change in phase. The second equation is Q equal to ml. Okay, this is the equation we use for change of phase, change in phase. For example, from solid to liquid or from liquid to gaseous state. Let's look at example 1. Okay, there are two parts. Part 1, you pour water into the beaker. The temperature of the water will fall and the temperature of the beaker will rise. The final temperature, theta, will be somewhere between 25 degrees Celsius and 40 degrees Celsius. If theta is above 37 degrees Celsius, the temperature of the aluminum block will rise when it is placed in the water. However, if theta is below 37 degrees Celsius, the temperature of the aluminum block will fall when it is placed in the water. So our strategy is to do this problem in two parts. Step 1, find the final temperature, theta 1, after water is poured into the beaker. And step 2, find the final temperature after the aluminum block is added to the water. Okay, for step 1, the amount of heat lost by water equal to the amount of heat gained by the beaker. So substituting values, theta 1 is equal to 38.0 degrees Celsius. So this is higher than the temperature of the aluminum block, which is 37 degrees. Therefore, when you put the aluminum block into the water, the temperature of the water and beaker will fall and the temperature of the aluminum block will increase. So substituting values, theta 2, that's the final temperature, will be 37.8 degrees Celsius. Example 2, this question is tricky because the ice does not melt entirely in this case. Whenever we have doubts about whether there would be a complete phase change in the question, we should be prudent to make some preliminary calculations to check if our hypothesis is true. Okay, for part A, the amount of heat needed to melt 5 kg of ice at 0 degrees Celsius is 1.665 times 10 to the power of 6 joules. The amount of heat released when temperature of 10 kg of water falls from 15 degrees to 0 degrees is 6.279 times 10 to the power of 5 joules. So since the thermal energy released by the water is less than the energy required to completely melt the ice, some ice will remain, and the final temperature will be 0 degrees. So for part B, let the mass of ice that melted be m. So heat gained by melted ice will be equal to heat lost by the water. So we already calculated the heat lost by the water as its temperature dropped from 15 degrees to 0 degrees Celsius. So the mass of ice melted will be 1.89 kg. Okay, let's look at example 3. Part A, the temperature during vaporization is the same for both trials. Therefore, the rate of heat loss to the environment is the same for both cases. So the power dq dt will be equal to the dm dt times L. Now there's another factor which is H, the rate of heat loss to the environment. Okay, rate of heat loss is actually a power. So for trial 1, we get equation 1, trial 2, we get equation 2. From equation 1 and 2, we are able to get the specific latent heat of vaporization to be 1.95 times 10 to the power of 5 joules per kg. So for part B, we substitute the value of L into equation 1, and then we are able to get the final values for H. Now note that depending on what value of L you put in, if you put in the calculator value with many significant figures, H will be 7.39 watts. But if you use the answer with 3SF, then H will be 7.47 watts. Okay, Cambridge will set both values, but you have to show your working very clearly. Microscopic view of energy. Okay, this is the energy related to the molecules within the boundary of our system. Internal energy is a very important concept for this chapter. The internal energy U is the summation of microscopic kinetic energy due to random motion of the molecules and the microscopic potential energy due to intermolecular forces. Okay, this comes to the end of section 1 and 2.